Hello, friends. Welcome back again. In this week 8, as we are exploring some of the 4D behavior of the materials, and in our previous discussion, we have one example in which we try to develop a exotic structure or a meta structure using a metal 3D printing, in which we explored the use of inconel and stainless steel alloy. Now, this is another example or a case study here in which we are using again the laser powder bed fusion, uh, specifically the direct metal laser sintering process, in which we are interested to basically work on two metals or the alloys which are having a huge difference in their melting range. If you see in previous case, I have the stainless steel and that is 174 precipitate hardened stainless steel and nickel 625, in which the difference in melting range was around 50 degrees Celsius, like 1250 degrees Celsius to 1300 degrees Celsius. But in this case, what we want to understand is what is the effect if I am using a two metallic alloy in which the melting temperature difference is to the tune of 400 to 500 degrees Celsius. So this work has not been reported earlier, in which the difference in high melting point is basically compensated using the concept of the exotic structure for a better joint strength, right? So that is the actual idea of using the exotic structure in these type of material with a high or the relatively larger variation in their melting temperature. So what we do is, in this case, we use two type of metastructure. One was dodecahedron and another was the octet. And the study suggests that the octet based metastructure has reported better than the dodecahedron. The reason is due to the smaller number of nodes. Let me understand it in a simple way. Like for example, if this is a one plate and this is the lower one, in which let us say the lower one has a lower melting and higher one has a higher melting temperature. Now once I am printing layer by layer and going step by step ahead, so if I put more links to the material which is having a higher melting and less number of links to the material which is having a low melting, then the net heat accumulation in a that plate surface will be less. So that will be helping me in basically controlling the net energy density or net heat effect, net heat accumulation, net residual stresses, you know at that particular functionally graded material. So that philosophy actually we used, and what we observed that we were able to generate a functionally graded material using this particular technique. So this is the idea. Like you see, and I think you can again see the small glimpse of how my metal printer work. Here is the video. You can see. Now, once you observe the functioning of metallic part layer by layer, the one basic thing we understand is once I have a building of the part, first there is a application of the support material. So this support I can select. I can think of a solid support. I can think of a support like a pillar. I can think of the support like a honeycomb, right? So here, normally by default by machine make a sport of around 2 mm. So up to this length there is a 2 mm sport. Then after this is a solid 17.4 pH stainless steel part that has been prepared up to 1.33 mm length. Actually this thickness that we are seeing totally, this is as per ASTM E8M. Basically I am interested to make a tensile coupon, so that thickness part we actually studied, right? So using the simple idea of dividing the total, let us say the 4 mm thickness into three zone, like 1.33 each, we divided it like for the first 1.33 mm, we will be using the 17.4 pH stainless steel part. Then in between you can see over here, here is a meta structure It can be a octet, it can be dodecahedron, it can be phyllon. In this case, the octet and dodecahedron is being compared. Now this part is the titanium, now if you just see the number of nodes at this location and this location are same like shown in this case, then the heat accumulation will be almost similar. But if somehow I reduce the number of links over here and increase at this position, then there will be relatively better position as regard to the cooling rate etc is concerned. So net heat accumulation at the low melting alloy will be better managed, because here it is going to have a melting temperature around 1300. Here if I am interested in making this titanium part something around 1700 degrees Celsius. So to compensate that, what I am doing is I am putting more links at the zone where I am having the capability of putting it at the high temperature, and here on the stainless steel part, as you can see, I will be putting less number of links, so I will be able to make a solid part. So this is a typical CAD file that we use as per ASTM E8M. Now you can see over here, this is the fabricated part. As you can see, the top is Ti6Al4V, the bottom part is 174 pH stainless steel, and in this case the dodecahedron metastructure has been applied over here. This is of course made up of the titanium, and we tried with the octet also, right? So this is the basic element structure of the dodecahedron. Now this is the basic structure for the octet. Similar to that, top titanium, middle titanium, lower one 174 pH stainless steel, and this is the actual printed part. So you can see this specimen with the octet metastructure. Here is the sport with 174 pH. Here at the top, this titanium part, there was a misrun during the printing. So specimen with the dodecahedron metastructure we were not able to actually print in a proper way, whereas with the octet this was suitably printed. Now if you carefully see this, this is the sport which will be of course with the removed with the EDM wire cut. This part, this solid part, as you can see over here, this is 174 pH. This is again Ti6Al4V, and the top is again with the Ti6Al4V. But this link is basically, as you can clearly see, the number of nodes on the lower part are less, whereas the connection at the top one are more. So this helped me in controlling the heat affected zone in a better way. So this is the again the view of 3D system DMP200 model that we are having in our lab for the printing of this type of the setup. So basically what we are doing, as we have seen in our metal printing case, I am interested to control basically the energy density, which is depending upon the directly proportional to the laser power, and on the denominator side we have a scanning speed, we have layer thickness, we have the hatch distance. So basically the simple empirical relation help me to control the energy density. So I have to work on a particular energy density, and then using that energy density, it is going to create a melt pool at this specific region. What I can do is I can play with the particular energy density value, but the net heat accumulation, because the more number of nodes basically that we can control. So that is the central idea of this case study, and successfully we were able to print these type of material. So specifically in all alloys or the powders that we use, what we need to understand is the rate of cooling, which can help me in directional solidification, right? And we can develop our own mathematical model or the formulation for these type of the hybrid or the functionally graded material. Now continuing this study, now this is the another example that I want to put in front of you. This is now using the nickel powder, nickel 625 and 174 pH stainless steel. Here the temperature difference is to the tune of 50 degree. So what we have done is we selected this material. Here the another important step that has been added, that is the development of the phase diagram. So basically, I am interested to know, like my, let us say, mechanical properties increasing, or mechanical property in some case is, let us say a young modulus is decreasing. Now, why this happens? So, for this purpose, we are interested to develop a phase diagram, right? This will be based upon the EDS that we will capture from the SEM analysis. So that help me in understanding why my particular mechanical property is increasing or decreasing, right? So we will see this. Then, of course, like the previous practice, we have already seen in our metal printing case, the powder preparation using sieving, oven heating, characterization, pre-print analysis using the laser powder bed fusion for the nickel 625 and 74 PS stainless steel. Then printing of these material. Then of course we can think of their characterization in terms of mechanical abrasion, wear, in vitro analysis. Again similar, the same setup. This is the scanner head, sintering piston, feeding piston, roller, scraper, etc. So these are the parameters that I normally play: laser powder, scanning speed, hatch distance, layer thickness. These basically we control for the laser powder bed fusion process. So here I am using the comparison of solid and the octet metastructure. So what actually we did is, we make the top layer with nickel 625, as you can see over here. The top is nickel 625. The meta is of 17.4 pH, and this meta is basically the exotic one, and the lower part is again of 17.4 pH. So top nickel 625, bottom 17.4 pH, and the octet part is again 17.4 pH. So once I have a fabricated part, we go for its SEM analysis, and based upon the SEM data, we have a EDS, and I got a elemental composition. Now this elemental composition that I have, now we put it into the thermocalix software, and with the help of the thermocalix software, we were able to generate these type of the phase diagrams. Like this is the phase diagram, as you can see, for 17.4 pH, and this is the phase diagram for nickel 625. So here I came to know that at which particular temperature there is a FCC formation, or there is a martensite formation, or there is a ferrite formation because of the BCC, or there is a some secondary carbide or some intermetallic phase, right? So these type of informations we got. So this actually help us in understanding the microstructural development in 3D printed part. So there are some critical phases that may affect the mechanical and thermal characteristics, like FCC, which is a austenite phase, and BCC, which is a ferrite phase, then FCC L12, which are some precipitates. So the in some cases the coexistence of compositionally different subphases like FCC A1, FCC L12, and their transition across the broad temperature range are of course available from this diagram. So when we specifically see the this diagram, phase diagram for nickel 625, what we observed that there is a dominance of FCC A1 phase, so which is basically responsible for exceptional toughness, ductility, and corrosion resistance. So what I need to understand is why I am getting a better result in vitro. So that basically we correlate with this. Why I'm getting a exceptional toughness, why I'm getting a better, let us say, strain, why I'm getting a more ductility. So which particular phase is responsible? Like for in case of nickel 625, this is FCCA1. This we are able to generate through the EDS data, and this is the experimental observation. So this helped me in a better discussion of my result, specifically that I am getting with my this type of material. So further, by strengthening the phase like FCCL12, NB, N13, DOA, P phase, this helps to improve the lye stability and strength at the high temperature. So these observations actually help me in developing a typical exotic structure. Why I am using this type of exotic structure, how this will be, affecting the phase diagram using the SEM and EDS analysis, and the combination of the different mechanical morphological properties, specifically the porosity part, that we can club together and can have a tunable Poisson ratio, can have a tunable Young modulus, can have a tunable modulus of toughness. So this is the beauty of using the different type of the exotic structure. I believe the information is helpful to you. So there are some more examples that we will be exploring in my coming video on use of these type of 4D printing applications for the polymer part as well as for the gel printing. Thank you very much and keep watching.